Hello everyone, my name is Yu-Hsin, and I'm a PhD student from Georgia Tech. Today, I will be presenting our combined experimental and modeling study that investigates how post-processing forming gas annealing impacts oxide semiconductor thin-film transistors. This work provides a comprehensive understanding of defect dynamics and BTI behavior, offering key insight into how thermal and hydrogen effect evolve during post-processing annealing. This slide shows the outline of my presentation, which is divided into 5 parts. Starting with the motivation of this work, understanding the impact of post-back-end-of-line FGA impact on OS-TFT. Oxide semiconductor TFTs, OS-TFTs, have recently emerged as promising candidates for high-performance M3D integration, owing to their excellent electrical properties and good back-end-of-line compatibility. However, during the M3D process, there exists a critical step, the forming gas annealing, FGA, which can severely impact OS-TFT stability. FGA is typically performed at the end of the back-end of line to passivate the dangling bond in front-end silicon logic transistor to enhance its reliability. Unfortunately, this hydrogen-rich anneal becomes detrimental for OS-TFT, as hydrogen can diffuse into the oxide channel, induce defect generation, and severe threshold voltage shifting. Now, let's take a closer look at the main challenge OS-TFT face under FGA. There are two critical issues here. First is the performance instability. After FGA, we often see a clear negative VT shift and even SS degradation. Second, the reliability degradation. Hydrogen can diffuse into the oxide channel during bias stress, effectively doping the channel and causing large threshold voltage shifting over time. In recent years, many studies have tried to tackle this hydrogen issue using two main approaches. First is the channel engineering, basically making the oxide channel itself more resistant to hydrogen, for example, using fluorine plasma treatment or doping modification. Second, the barrier engineering, to develop a suitable hydrogen blocking layer. However, despite these efforts, there's still no direct, comprehensive study that clearly reveals how post-processing FGA impact OS-TFT performance and reliability. A systematic understanding of this critical process step is still missing and urgently needed. This brings us to the highlight of this study. In this study, we have two main highlights. First, we propose a thin hybrid capping layer that demonstrated complete hydrogen immunity under 400C FGA, maintaining both device performance and VT stability. Second, using this optimized device platform, we integrated comprehensive electrical measurement across all FGA durations, together with DFT modeling, to reveal a clear, unified picture of the defect dynamic that actually occur during post-processing FGA. Altogether, these findings will provide critical insight for integrating OS-TFT to back-end of line process flow. First, I will introduce the experimental part of this study. This slide shows the 3D schematic of OS-TFT with optimized hydrogen barrier, together with the TM image of the channel region. The gate oxide is a 5 nanometer hafnium oxide layer, and the channel is a 3.7 nanometer tungsten-doped indium oxide film grown by ALD. The contact of palladium. For the hydrogen barrier, we designed a hybrid bilayer, 3 nanometer hafnium oxide underneath and 3 nanometer aluminum oxide on top, both deposited by ALD. The hafnium oxide interlayer prevents post-capping degradation, since we found that directly depositing aluminum oxide could shift the VT. The aluminum oxide layer, on the other hand, provides excellent hydrogen blocking capability. Finally, the complete device underwent post-processing FGA at 400C, closely matching the back-end of line integration condition. Now, let's look at the impact of post-processing FGA on our device. This figure shows the transfer curve of OS-TFT with optimized hybrid capping, annealed at 400 C from 10 minutes to 60 minutes. A slight VT shift is observed during the first 10 minutes, after which the threshold voltage remains stable, even with prolonged annealing up to 60 minutes. The right two plots summarize VT and SS trend across different durations. Thanks to the strong hydrogen barrier from aluminum oxide, even as the thickness is reduced from 19 nanometer to 3 nanometer, VT remains stable and SS improves consistently. To separate ambient hydrogen effect, we also perform a pure nitrogen anneal shown in this figure. Similar behavior under both FGA and N2A confirms that the change are thermally driven, not by hydrogen ingress. Interestingly, we notice a distinct kink feature at deep subthreshold region after 10 minutes of anneal, appearing both in FGA and N2A. This feature gradually disappears with longer anneal time. The kink behavior also shows up in the multi-frequency CV. After 10 minutes of FGA, we see the kink occur at lower frequency, but as anneal continue, kink fade away. This suggests a transient process of intermediate defect state that form and then stabilize over time. To better understand the origin of this kink, we perform numerical simulation using the Genestra platform, which show excellent agreement with our experimental data. As shown in the first figure here, we introduce a Gaussian distribution of shallow donor state near the conduction band minimum and located close to the gate oxide IW interface, successfully reproduce this kink. This confirmed that the 10-minute FGA kink originate from an increase in shallow interface state. This effect is highly sensitive to defect density, energy level, and spatial location. This shallow donor state promotes trap assist transport, especially in the deep substrate region, where carrier can thermally excited from trap state to conduction band, leading to this early turn-on behavior we observe as the kink. Next, we conduct a comprehensive reliability study across different FGA duration at room temperature 55 C and 85 C under a fixed overdrive voltage. The data here shows the NBTI result, and the measurement waveform we use is illustrated in the diagram at the bottom. Before FGA, the device shows a negative delta VT, which originates from the field-induced ionization of oxygen vacancy in the channel. This vacancy releases electron during negative bias stressing, making the channel more conductive, hence showing negative delta VT. However, after FGA, we observe a polarity reverse of delta VT from negative to positive, and this effect becomes stronger at higher operation temperature, with longer FGA 30 minutes and 60 minutes. The fourth figure here summarizes the delta VT via different FGA duration. This polarity reverse of delta VT from negative to positive is due to hydrogen diffusion, what we refer to here as intrinsic hydrogen. Since we already proved that our device is immunity to annealing ambient hydrogen, we believe this intrinsic hydrogen originates from the palladium context, which can absorb and release hydrogen during fabrication process due to their high catalytic activity. When stressing the device, this intrinsic hydrogen diffuse plays a role. Now looking at the PBTI data, we again see a similar polarity reverse of delta VT after FGA, from positive to negative, which also linked to diffusion of intrinsic hydrogen. But there is something more interesting here. After 10 minutes of the FGA, a strong negative delta VT appear, which then gradually weakened with longer annealing. This behavior is because of partial crystallization of the oxide channel as FGA continues. Once the film begins to crystallize, the hydrogen tends to form strong OH bond at the crystalline amorphous interface, effectively locking it in place and reduce hydrogen motion. As a result, the negative VT shift becomes smaller over FGA time. We will revisit this later after discussing the modeling section a complete BTI mechanism will be summarized. To further confirm that the effect doesn't come from ambient hydrogen, we also perform BTI measurement on control device anneal in pure nitrogen at 400C. After 60 minutes, both PBTI and NBTI show similar trend to the FGA case, confirming that the observed behavior originates from intrinsic hydrogen rather than from the ambient. Next, let's move on to the modeling section. Based on our DFT and molecular dynamics simulation, we found that two distinct stages of defect dynamic occur during the 60-minute FGA. The first stage around 10 minutes corresponding to film densification. The second stage is the partial crystallization with longer anneal. Let's start with the stage 1, where densification takes place during early phase of FGA. This slide shows our DFT and MD result connecting defect energetic with structural density in indium oxide. On the left, the low-density indium oxide network exhibits large void and many 3-coordinate oxygen atoms, which leads to highly localized and deep defect state, where here the energy of localized defect is lower. As the density increases, but still below the crystallization region, the void diminishes and the network grows more connected, dominated by 4 coordinate oxygen atoms. The higher coordination promotes the formation of oxygen vacancies, which act as a shallow donor state. As we can see here, the energy of shallow defect now is lower. This will enhance electron transport. In short, densification suppresses localized trap and favor shallow state formation, which will increase carrier in the channel. This is the statistical analysis of AT-independent MD simulation at 2 different indium oxide density, which provide a more clear picture of how density affects defect behavior. At low density, most defect states are highly localized and lie deep below the Fermilevel. In contrast, at higher density, a larger fraction of the defect becomes shallower and the formation energy decreases. So this trend confirms that densification promotes shallow state formation, consistent with our experimental observation that the first 10 minutes of FGA, shallow donor state emerge, giving rise to the kink behavior in the electrical characteristic. Now, when the FGA is prolonged, it will enter the second stage of defect evolution, where partial crystallization occurs. The GIXRD result clearly indicated that our oxide channel undergoes partial crystallization after 60 minutes of FGA. We observe a pronounced increase in the intensity of 440 diffraction peak, while other peaks remain largely unchanged. As I mentioned earlier, although we rule out the impact of ambient hydrogen, intrinsic hydrogen still play an important role. From our DFT insight, this intrinsic hydrogen tends to localize near crystalline amorphous interface. Hydrogen can bond in 2 distinct ways. First, it can passivate metallic indium-indium pair and form an ionic indium H-indium configuration, which act as a shallow donor state. Second, it can form a strong covalence bond with oxygen, forming OH bond. This will leave adjacent indium-indium pair, which itself is a deep localized electron trap. From the left figure here, we can see that both types of hydrogen-related defect have lower formation energy in the amorphous region, indicating that this hydrogen incorporation is more favorable here. And if we look at the spatial diagram here, the indium OH complex are preferably formed at the crystalline amorphous interface, suggesting that hydrogen is likely to diffuse and pinned at grain boundaries once partial crystallization happened. Now, by combining the electrical result with DFT modeling, we can now outline the full BTI mechanism during FGA. This is the PBTI trend we observe at different FGA durations. Before FGA, we only see a small positive delta VT, indicating there is a limit charge trapping effect. After 10 minutes of FGA, intrinsic hydrogen increase, and under positive bias stressing, H- and H neutral charge state dominated. In our simulation result here, H neutral shows frequent indium to indium hopping, and this hopping can passivate indium-indium pair and form shallow indium-H-indium donors. This donor will increase carrier in the channel, leading to a strong negative delta VT. With prolonged FGA at 60 minutes, partial crystallization happened, and that means the crystalline amorphous, the Ca interface increase. This will trap the intrinsic hydrogen as the OH bond, limit the intrinsic hydrogen motion during the stressing, and reduce the negative stressor voltage shift. In short, early FGA activated intrinsic hydrogen to form shallow donor state, while prolonged FGA locked the hydrogen at the Ca interface. Result is the smaller delta VT shift. On the NBTI side, before FGA, the device shows a negative delta VT, originating from the field-induced ionization of oxygen vacancy in the channel, making the channel more conductive, hence shows negative delta VT. As the FGA duration increases, delta VT gradually shifts from negative to positive, and this effect becomes stronger at higher operation temperature. This happened because under negative bias stressing, H+ charge state dominated. H+ tend to form strong OH bond as seen in our simulation here. With longer FGA, partial crystallization generated more Ca interface that will provide a favorable site for the OH bond to form. Once the intrinsic hydrogen is locked at this interface, more indium-indium trap remain unpassivated. This acts as the localized electron trap and hence reduce the channel conductivity, and that shows a positive delta VT. Lastly, let me give a brief summary and highlight the key takeaways from this work. Here are the 4 main takeaways from this work. First, we demonstrate a robust strategy, the hybrid capping approach, that effectively maintains OSTFT performance even under 400C post-processing FGA up to 60 minutes. Second, we gain deep insight into how electrical characteristics evolve under FGA, particularly the emerge of the Kink and the BTI trend. Third, through DFT modeling, we identify a 2-stage defect dynamic, starting with the densification and followed by partial crystallization. And finally, by combining experimental and modeling, we establish a comprehensive BTI mechanism that explains the behavior of the OSTFT during post-processing FGA. I'd like to thank all our funding organizations, the SRC GRC NMP program, Samsung Electronics, U.S. Department of Energy, and the National Science Foundation. Thank you so much for your attention.